Hello everyone. So today, so previously we had discussed on the topic heavy light decomposition algorithm, right? So how we can make use of it within the this one with the segment tree as well as the fin tree that we saw, right? So that is one of the important this one algorithms, very important algorithms. So today what we'll be doing, we will be discussing on the topic centroid decomposition algorithm, right? So let's get into the definition part here. So what does the centroid decomposition algorithm say here? Centroid decomposition is a divide and conquer algorithm. This part is very important. It is a divide and conquer algorithm on the trees, right? What it does, it recursively, right? It recursively breaks a tree into the smaller subtree using the centroids nodes, right? That balance the trees such that no resulting subtree has more than half the total nodes. So, mainly, I would like to tell you one thing. We are solving the problems on the centroid or the middle of the this one middle node of the tree itself. Currently, on the Codeforces, we are solving the problems that uses this algorithm as well. We have made use of this particular algorithm as well. While solving the DP problem as well, DP on trees, if you remember, we had made use of the centroid, something called centroid calculation and all, right? So the same algorithm we had made use of earlier. If you can just check the DP, this one, what do you call dynamic programming playlist, we have made use of the centroid decomposition algo there. Yeah. Now also we are solving the problem on the centroid on the within the graph basically. Now we are solving the graph problems, right? So we are solving the problems on the centroid or this one middle node, right? So that's what I wanted to say. So this is one of the important algorithms. What it does, first of all, centroid decomposition is a divide and conquer algorithm on the trees, right? It recursively breaks a tree into the smaller subtrees using the centroid nodes that balance the tree such that no resulting subtree has more than half the total nodes. So this is helpful in this way, right? It's mainly used in the, again, this is used in the path queries as well. Similarly to the this one heavy light decomposition, it is mainly used in the path queries, tree distance problems, and the optimization on the trees. Again, so whenever there is intense optimization needed, we'll be going with a centroid decomposition usually. So heavy light decomposition as well, mainly the segment tree fin tree part. Whenever we need this one intense optimization, then only we'll be making use of it, right? So it's mainly used in the path queries, tree distance problems, and the optimization on the trees. Simple. Now let's get along with the this one explanation part. Let's move on with the explanation part here. So first point here is a centroid of a tree is a node that when removed, it splits the tree into subtrees with each with at most n by 2 this one nodes, right? Simple. A centroid of a tree is node that when removed, when if we try to remove that node, it splits the tree into subtrees, each with at most n by 2 nodes, half nodes, n by 2 nodes, right? So this is fine. Now the centroid decomposition recursively, what it does, it finds the centroid of the current tree. First, it finds the centroid of the current tree. First main thing. The second thing is it removes the centroid to divide the tree into smaller parts. Second thing, it removes the centroid to divide the tree into the smaller parts. This is the divide and conquer algorithm, right? Quite obviously, it removes the centroid to divide the tree into the smaller parts. The third one here, it repeats the process on each subtree. So just keep this and keep these three things in the mind, right? So finally, let's come to the last point here. This forms a centroid tree which can be used to solve problems efficiently that are otherwise expensive on the original trees, right? Example also, this one I have found this one useful. So some of the examples I have considered here: shortest paths, subtree queries, etc. Right? So this is fine, I believe. Now let's do one thing. Now we have the understanding of the algorithm, what it does. Let's try to implement the same thing or understand the same thing by writing the algorithm, or let's try to implement that one in the form of code basically, right? So first, what shall we do? I'll just go with from collections. Let's import the default tick. We'll be making use of the default tick. So I'll be going with the default tick. This is fine. Let's come to the first step, man. So we'll what do we do? Let's go with the different steps. Let's go with the first step here, right? So first step here would be we have to, or we will be building the adjacency list for the tree. So that is the reason we are importing we have imported the default dict actually. So I'll just go with the default dict of the list, right? So this is fine. Now let's consider the example tree edges, right? So we'll be going with the example usage later. So now itself let's consider the example tree edges. So I'll just go with the edges equals. So this one, let me consider here 1 comma 2. This is fine. 1 comma 3. This is also fine. So this has to be within the parenthesis. Yep. Now let me go with simple one. 2 comma 4 as well as the 2 comma 5. So 3 you can, what happened here? Oh yeah, this one need give closing parenthesis here and opening parenthesis here, not the arrow. Sorry, this one square bracket here. This is fine. So I'll just draw this one and show you, man. So this is similar to this one. From 1 to 2, 1 to 3 we are considering. So 2 to 4 as well as 2 to 5. So this is the tree we are considering, right? So just keep this in mind. So let me delete this one for now. You can just pause the video and look into it. I have considered the simple one, very simple one basically, right? So let me go with the iteration part here. U comma V in the edges. We are considering the edges, so we'll be going with the U and V, right? So again, now we'll be going with the G of U. Uh, we have to append the second edge, right? So we have to go with the V basically. So this is fine. We have to go with the V. Then G of V. Let me go with let's append U here. This is fine. Now let's do one thing. Let's move on with the next step. So in the step 2, what we'll be doing, we'll be initializing the helper arrays. So n, let's consider the 5. So we have 5, this one, edges, right? Not the edges, basically what we call vertex, right? So this one, see, 1, 2, 3, 4, 5. We have n equals 5, right? So this is fine. Now let me go with subtree size, right? So here, let me write it in this way. Subtree size variable name. So this one initially 0 into n plus 1. This is one indexed, right? So this is fine. Also, we have to mark the visited as well. I'll be making use of the visited. Initially, this will be set to false into as it is one index. Let me give n plus 1 here, right? So this is it for the second step. What we have done here, we have just initialized the helper arrays. Next, let's go with a function to compute the subtree sizes. We have to compute the subtree sizes, right? So after getting the centroid, this one, the center node, we have to write the function quite obviously to compute the subtree sizes. So I'll just go with the def here, dfs sizes u comma p. So this is fine. The next step would be subtree size of u is equal to 1. Now let me go with a for loop here for v in g of u. This is fine. Let's go with a simple if condition. If v not equal to p and not visited of v, then subtree size of this one u equals subtree size of u plus. So we'll be going with a DFS sizes. So have I considered DFS sizes? So this one has to be DFS size of this one. Have to go with a v comma. This is fine. Finally, let's return this one. What do we call? Let me give return here subtree size of what? Of u, right? So this is fine, man. We have successfully returned the function to compute the subtree sizes. Now let's do one thing. Let's write the function to find the centroid of the tree. Quite obviously, we have to write the function to centroid of the tree. Find the centroid of the tree, right? So I'll just go with a function name. Let me go with find centroid itself. So this will be good, right? So I'll just go with find centroid. So let me go with u p So this one will be total underscore nodes. So this is fine. So now for v in c of u, then this for loop, let me write the simple if condition. If v not equal to p, and so this one not visited of v, and subtree size of v, this one, if it is greater than total nodes by 2, then what we will do, let's return something, man. I'll just go with return find centroid. So this one will be v comma u and total nodes, right? So this is fine. Let me go with return u, right? So this is fine. Yep. Now let's go with the this one more function, right? So this will be the last function basically. What we had discussed in the approach, this one explanation. So we will be going with the recursion, right? So that is nothing but the recursive centroid decomposition. Let's move ahead with the recursive centroid decomposition. I'll just name the function here decompose. So this will be better. This suits here, right? So decompose, yeah. So I'll just go with you and the parent, right? So this is fine. Now let's compute the sizes for the current tree first. So I'll just go with total here. So nodes DFS size of this one u comma -1, and let me go with not the credits one. We haven't written centroids. We have, right? Oh, this is the newer one. Just give me a second here. In the Python, we don't mention the data type one. Right? That is the which disadvantage. This is fine. So Centroid, I type Java code this one a lot. So feels completely weird sometimes. Sometimes I feel weird when typing the Java code, and sometimes I feel weird when I'm typing the this one Python code. And sometimes I feel extremely weird when I'm typing the JavaScript or the TypeScript. This is fine. Now let me call the find centroid function here. So we have to pass u comma -1, and let me go with the total nodes here. This is fine. Yep. Now let me go with visited keyword. So this one visited of centroid. Let me assign this one to the Boolean value true. Where is this? True. Yep. Now let's write, let's make use of the print statement for the interactive purpose. So we'll be making use of the string interpolation. Let me start with if here. Right. So I'll just go with centroid found. So we are just what we are doing basically recursive. We are going with the recursive centroid decomposition itself, right? Recursive centroid. So I have made use of the this one centroid variable. I believe this one. Yeah. Let me copy this one. Let me paste it over. Yeah, centroid. And let's do one thing. I'll just go with a parent. So parent, we are going with a parent itself, I believe. So let me pass here parent, right? So this is fine, man. Yep, parent, we have passed this one as the parameter here. This is fine. That's what we are considering here. This is fine. This is it, right? So now after this, what we need to do, we have to recur on the subtrees. So we have to go with the recursion on the subtrees formed by removing centroid, right? So for that, let's go with the this one iteration v n g of we have to pass the centroid, right? So this is fine, easy peasy. So now I'll just go with if not visited of this one v, right? So next what we will do, let me call decompose here. We are just recurring here. So what are the things that we need to pass here? V along with the centroid. Yep, simple. Now the final step is we have to start the decomposition from the root node. Here the root node is quite obviously 1, right? So we have 5, this one, what do we call? Vertex 1, 2, 3, 4, 5. Edges also we have considered example here already, right? So this one I'm speaking of. n equals 5. We know this one, right? So see here, this is fine. Finally, let's start the decomposition from the root node 1. So I'll just go with decompose here. So let me pass 1 comma minus 1. This is fine. We are done with the centroid decomposition algorithm, right? We are done with the centroid decomposition algorithm. Yep. Now, yeah. Now, before running the code, so let me explain the algorithm so that we don't forget, right? So here, first we have made use of the default dict here. What it does, basically, it lets us create the adjacency list representation of the tree. We have discussed this one. We know. So now we are going with the edges array. This one. This is nothing but it defines our tree connections, right? 1 to 2, 1 to 3, 2 to 4, and 2 to 5. I have shown the this one by drawing that one, the tree, right? So this is fine. Now we are going with the subtree size. Basically here, this one, the line number 31. So what it does, it keeps the track of the number of the nodes in each subtree. Then we are going with the DFS size function. So this one I'm speaking of, right? So this one line number 34. So what it does, the function DFS size computes subtree sizes recursively using the DFS. Then we are going with a find centroid, this part. So this function recursively finds the node such that none of its subtrees exceeds half of the total nodes. This is also fine. Next, let's go with the decompose function. So what it does, it computes the subtree sizes. This is one of the thing, and it finds the centroid as well. It marks the visited, the one which is visited. Basically, it marks it as visited, so we don't have to visit that one again, right? Finally, recursively, it decomposes each subtree found by removing the centroid, right? So finally, we have called here this one decompose of 1 comma minus 1. This starts the decomposition from the node 1, right? So this is it. Simple one. We are done with the algorithm, right? So now what is the output that we need to get? Let me come to the example part. So we have considered here, just give me a second here. 1 second. Yeah, we have considered the edges here, 1 to 2. 1 second. I'll write down this one. This one, let me write this one fast. Right, so just give me a second here. Now, yep. So basically, centroid found. So we are going with a 1 2 1 3 2 4 2 5, right? So centroid found is the thing that we are giving at the end, right? So this is fine here. See line number 51. I'm speaking of. So we are going with the centroid as well as the parent we are displaying, right? For this one, centroid found is 2 initially, right? Centroid found is 2. Right? So this one centroid found 2 initially, and the parent is minus 1. And the parent is minus 1. Just give me a second here. Am I going wrong? Yeah, this is correct itself, man. See, first of all, we have written the algorithm. The algorithm, what it does, it finds the basically it first identifies the node 2. This one, node 2, I'm speaking of. It identifies the first node 2 as the main centroid because basically removing this node 2, right? It splits the tree into balanced parts, right? 1, 3, 4, 5. You can clearly see it splits the tree into balanced parts. Then we have the smaller subtrees. What are the smaller subtrees? We have 4, 5, then finally 1 and 3, right? So this is fine, I believe. These are decomposed recursively. We know that, right? Each subtree centroid is printed with its parent centroid. That's what we are doing here within the print statement, line number 51, right? Forming the centroid tree structure. Next, we have, after removing this one, centroid found is 4. The subtrees we have to consider, right? Parent is nothing but the 2 for this. For all this, basically removing this node, what it does, removing the node 2 as the main centroid, we are removing the node 2 as the main centroid because removing it splits the tree into balanced parts. So for every this thing, other this one node that we consider, so 2 will be the parent, right? So I can just write 2 4 times here. So 4, what we need to consider, what are the left nodes basically? 4, 5, 1 as well as the 3, right? 4, 5, 1 as well as the 3. First, for the first one, the parent is minus 1, right? So this is fine. Now we have got the output, this one, right? Accordingly with the what example that we have considered. So the output that we need to get here is centroid font 2 and this one parent minus 1. So that's what we are displaying here within the print, right? Centroid found 4, 5, 1, 3 respectively, and the parent is 2 for all the subtrees. 4, 5, 1, 3. It is 2, 2, 2, 2 respectively, right? So this is fine. So now we have the idea on this one. What the output? What is the output that we need to get? So let me do one thing. Let me give Control J. Let me come here. Let me give Control J, and let me right click. Let me copy the this one. What do we call name? I'll just give here Python. Let me give a Centroid decomposition. This one file name.py. This one has to be multiplication symbol, man. Most of the times I type wrong this one. Where is this line number 31? 31, 31, 31. Yep. So again, 31 and 32 both. So this one has to be multiplication operator. So let me give clear screen. Let me run this one again. So yeah, Centroid found 2 parent minus 1 followed by 1, 3, 4, 5. Right. So we are getting the different output, right? So here, let me do one thing. Yep. Oh, so here, this one indentation problem. This one return statement I have given within the for loop. So let me remove this one out of the for loop, right? So let's do one thing. Let me give clear screen again. We run this one. Yeah. Now, now also we are getting the same output. What's wrong here? So this output is also correct one. So this was there was a bug here. So basically, this worked fine even though there was a bug for this particular case. So this is also one of the valid outputs. So we can have the multiple outputs here in this case. So this is also one of the valid outputs, right? So in this case, after this one for the 3, we have considered the parent one. That's it. So this is also one of the valid output. So we are getting the desired output. We are getting the desired output, right? So this is it for the centroid decomposition algorithm, right? The simple one, right? So now let's do one thing. We are done with the centroid decomposition algorithm, right? So next we'll be discussing on the topic. So Euler-Tour technique, right? So we'll be discussing on the algo Euler-Tour technique, right? So for now, this is it about the algo. So let me summarize whatever we have learned so far. Just try to remember these 3 to 4 points, man. This is very important. So the first thing here would be centroid decomposition breaks a tree into the balanced subtrees recursively. What it does, it breaks the tree into the balanced subtrees recursively, right? Each centroid, what it does, it ensures no subtree exceeds half the total nodes. We have discussed this one. This is one of the very important points you have to remember. First thing is, the first one is centroid decomposition breaks the tree into the balanced subtrees recursively. So that's what it is doing here, right? We have considered the node 2 when it is removed so that we can consider other subtrees balance, right? So we can consider the parent 2 as well for this one, right? So that also works, not a problem. So each centroid ensures no subtree exceeds half the total nodes. This is fine. Now, it is useful for solving complex tree query problems like whether it may be distance or the path queries, right? So whether it may be distance or the path queries in time complexity because of log this one, sorry, because n log n time, right? So because n log n time complexity. So this builds a centroid tree which simplifies many tree-based algorithms. This builds a centroid tree which simplifies many tree-based algorithms, right? So this is it for the, what do we call, centroid decomposition algorithm, right? So this is it for the centroid decomposition algorithm. Yep. Now, this what it does, basically the last point, this builds a centroid tree which simplifies many tree-based algorithm. This is fine. So this is it for the what centroid decomposition algorithm, right? So we are left with only the last 2 algorithms. One is, as I've said, next we'll be discussing on the topic Euler-Tour technique, and the final one would be square root decomposition on the trees. So the next, as I've said, we'll be discussing on the Euler-Tour technique, right? So for now, this is it. Thanks for watching, guys.